Have you been taking my advice on the roadmaps? I hope so. This is what it might look like when it's closer to done. Some of these will be filled in throughout this lecture, all these interconversions between the different types of carboxylic acids. But so far you should have filled out a roadmap for reductions and oxidations, right? So interconverting between alcohol, aldehyde, carboxylic acid. But as we go along, you're going to have lots of independent, look at how many separate reactions these are, but to see them connected in one grid is a lot more helpful sometimes for keeping them straight and seeing the patterns. So I might refer to this to kind of keep track of where we're at. We're going to work our way through these conversions. Okay. First, since we are in the carboxylic acid chapter, we always revisit nomenclature when we have a new functional group we're really focusing on. And kind of the star of this section is the carboxylic acid. And so we are going to focus on how we name a carboxylic acid containing compound. So let's see, I got to move this guy out of the way. There we go. All right, so when we have carboxylic acids, you find your parent chain is normal. Carboxylic acids have really high priority. They're usually at the top of the priority list. So even if other functional groups are present, carboxylic acids will win because they're the higher oxidized. And that's usually the only pattern that really makes sense out of that priority system, but it's something you can remember. Otherwise, you might have to refer to a chart or reference to see who has the highest priority. But carboxylic acids, it's easy. They're higher priority than anything else we've done. So they will automatically, because they are the higher priority, they will be the suffix. So oic acid, you don't need to worry about the prefix because it's rare that it will ever be a lower priority than anything else. So for example, this molecule has alkenes, which is something we've named many times before, an alkene, excuse me, but also has a carboxylic acid. This wins, suffix. Alkenes end up being, remember the infix. So let's give this one a name. First, we have to count the longest continuous chain of carbons. And number one always goes to the highest priority group. So carboxylic acid, 1, 2, 3, 4. And I'm not going to go off to that methyl because that would only give me 5. This will give me 6. So we're going to have a hex parent. But instead of hexane, it's going to be hexene because there's an alkene. Remember, that gets that infix position. We drop the E because the suffix only is there for an E if it's an alkane or a simple alkene. But we have another group. We have the acid. So oic acid is our suffix now. Now we have to describe, just like usual, anything else. The methyl's there. We have an alkene, right? So where is that alkene? It's on carbon 3. So we could put it right before, or we could have said hex3ene, oic acid. So either one of those are acceptable. We also have a methyl. Methyl happens to be on 4. Okay, so if I show someone that, they might say, okay, so in other words, you mean if I have a 6, 5, carbon 4, there we go, and then I have 3, 2, and 1. There's my molecule, right? And 4 has a methyl. Okay, I drew that structure. However, that means if you look closely, these are not the same. Notice how the methyl is on the same side as the carboxylic acid here, and here they're on opposite sides. So remember, with pi bonds and alkenes, it's just a good reminder not to forget your stereochemistry, your designation of E and Z. So you find when you have a pi bond and it has more than, it's not symmetric or it has groups that set apart its priority, you have to look at each carbon and establish which one has the highest priority on each carbon. So if I look at carbon 3, helps to draw on the H's. So we'll do this for both because it's a good review. Between H and this carbon that has a carboxylic acid attached, between those two groups, on carbon 3, carbon 2 wins over the H, right? So I'm going to circle the higher priority group. On carbon 4, we have an ethyl versus methyl. We know ethyl is going to win. So those are opposite each other. So those would be entgogen or E. Let's do the same analysis on the other one. Higher priority group there, higher priority group there, same side, Z. Okay, so we're not done with the name, Z, and now we're done. So it all comes back, right? You want to also be able to draw the structure from the name. Okay, so I'll let you do this as practice. We're going to think about our carboxylic acid derivatives and think about what's attached. Remember, they can do an attack open close kick mechanism, which means that when we kick something off, it's a leaving group. And what do we know about leaving groups? Leaving groups have to be reasonably stable to actually leave. So, in other words, good leaving groups are, think about it, strong bases or weak bases. Well, strong base is reactive, therefore high energy. Weak base is low energy because it's less reactive, more stable. So a good leaving group, something that's more willing to leave, is a weak base. So when we think about it that way, we think about the fact that we're about to close and kick something off. That's one way to establish a ranking for a predicted reactivity of these derivatives. So if you think about acid chloride, for example, the leaving group is chlorine. What does it look like when it's kicked off? It looks like chloride. We know that's actually a decent leaving group. What about acid anhydride? When that kicks off, it actually kicks off an acetate. That's a decent leaving group too. Look at that resonance stabilization. That's a weak base, right? But then with an ester, you kick off an alkoxide. Now we know that's actually a reasonably strong base, and then even worse would be like amines, and that would be kind of comparable to a hydroxide, by the way. And even worse would be like the amines. When that leaves, we have something that looks like that. So in terms of leaving group ability, this is, let's talk about stability or better leaving group. Right? And actually this is significantly better. So in other words, if we know that the leaving group of chlorine is a really good leaving group, who do we expect to be most reactive? And so it's actually in that order. Let's say, because it's basically a Caryo analysis, right? So the atom chlorine wins out over the oxygen and nitrogen in terms of holding that negative charge. So bring that back up from the Caryo chapter. But think about applying this to the reactivity. So that's after it leaves. So this is the stability of leaving group. So chloride is the most stable. But now let's convert that to what did it look like before it left? Okay, so before the leaving group left, we had acid chloride. So before chloride, it was acid chloride. Before acetate, it was acetic anhydride. Before alkoxide, it was ester. Before amide, amide and amide have the same name. Because think about that, amine, you drop the ene to make an ide, so amide. But it pronounces amide in different regions of the world. So amide is really the anion of amine, and amide is what Americans would call this group. But UK, I know at least, they pronounce it amide, and then that presents a problem with the anion. So they're spelled the same way. That's why it's confusing. Amide, amide. So that's in other words, that's an amide. But I don't like to dwell on that because we're going to see this functional group much more often. So that's kind of the difficulty with that one. But this is an alkoxide, which does not present a problem at all. Referring to that one, which had an ester before. Okay, so when we think about those, if we know that this is about to have a stable leaving group leave, that means that this is actually not stable. It's more reactive, right? Because if this is stable It's kind of like the caryoanalysis with acid-base. So you have a strong acid or base, you have a weak conjugate acid or base. It's a similar idea. You have a stable molecule and a good leaving group. That doesn't really make sense, because if it was a good leaving group, why didn't it leave? Why didn't it react? So we have a good leaving group, therefore a less stable molecule, because it's ready to dissociate, right? So it's the opposite trend. So let's call this, I'm not going to do the arrows opposite, but we really care about the reactivity. So acid chlorides are the most reactive, acid anhydrides are next, then esters and amides. Now, keeping this all in perspective, that also means that if we could assign the delta plus, which you can with computational chemistry, right? You could see, I'm going to do it in blue, since we know the blue means electron poor in that sense. The delta plus that would be on this carbon would be more blue, if you will. So I'm just going to try to make it, visualize that with a bigger one. This would be slightly more, but it's got a lot of electron-rich groups in there, kind of affecting its reactivity. Same here. So this is no different than an ester, really. And then finally, nitrogen, you can imagine, contributes more to make this even less. Okay, so that's another way to look at the same thing. All right, so we're going to do that in order. So not only is there a roadmap here, there's also a ranking of reactivity. So since acid chlorides have the best leaving group there, let's write that out. Best leaving group, it wins. What that means, though, is bad news for you at the beginning is we have lots of reactions for acid chloride. They can do everything. Everything the others can do, acid chlorides could do better and faster. So they can do everything because they're so reactive. So we are going to learn a lot of, when we do acid chlorides, then we're going to go to acid anhydrides, then we're going to go to esters, then we're going to go to amides. We're going to do lots of parallel reactions. Well, what about if I do that reaction to this one? What about if I do that reaction to this one? You'll notice as we get our way down the reactivity chain, there's less to do. So fewer reactions to write out. We're starting at the top. The most reactive is going to be able to do the most reactions. That makes sense, right? So let's show that conversion. So acid chloride, we're going to show how to convert it into all of the things. We'll start with acid anhydride. So acid anhydride, notice what we have over the arrow here. That should look familiar. Don't be intimidated by the charge. You're too mature to let acid-base chemistry intimidate you. What is that? If that is negatively charged, it's missing an H. So that means some base was added. Who was there before? Carboxylic acid. So in other words, you need a carboxylic acid. So normally you wouldn't start with the carboxylate, right? You wouldn't start with the carboxylate. However, you need one to do this reaction. So you're either going to see it written like this or with the acid already still intact plus base, okay? So because that's why we're using the base. We're using the base to deprotonate the carboxylic acid. Once the carboxylic acid is deprotonated, then it's ready to react. And actually, I have a space for the mechanism below, so I won't do it. So there you have it. We can make an acid anhydride. So you see we have this piece here, belongs to that piece. This piece here belongs to that piece. So let's see how that works. Well, with real R groups this time. Draw the mechanism. All right, if you're going to draw a mechanism, you want your lone pairs. And then I'm going to make it the extra step just so you're ready for all scenarios. So let's pretend it's still a carboxylic acid. Let's put some pyridine in there. That's a favorite base because it's a bad nucleophile. You don't want it also attacking. So what's going to happen first is that this mix gives us the carboxylate. Okay. And then draw on your lone pairs, get ready to attack. Attack, open. All right, now we have an isopropyl attached to the carbon that opened up. It's carbonyl. Still have our chloride, new group. I got that there. All right, so we can see progress towards the anhydride. It's a short, base conditions are pretty short mechanisms, as you know. Not a lot of, there's an opportunity for the proton transfer. Close, kick. So we have the attack, open, close, kick. Okay, so when you have a leaving group, you have the AOCK again. That helps us keep the carbonyl. So we should have predicted that mechanism even without doing it. We must, because carbonyls do one of two things for most of this chapter and the previous, attack open protonate or attack open close kick. And if it's attack open protonate, you have an alcohol. If it's attack open close kick, you have a carbonyl. We have a carbonyl because we know we're going to make an acid anhydride. So let's get the other group in there. So notice that's methyls from this one, isopropyls from this one, and we're done. Easy, right? In fact, the rest of the mechanisms are pretty simple, but there's a lot. So buckle down, have your roadmap out to check things off as you go along or fill them in. So for example, how would you do that? I'd get this picture back and I'd say, what did I just do? Can I make sure I know how to do all of these? I went from an acid chloride to an acid anhydride. Check, right? So it's worth kind of orienting yourself on this as you go. Okay. Time to do the next one. They can make carboxylic acids. Okay, so what do we need to make the carboxylic acid? Notice the pyridine back over the arrow. Okay, let's take a minute to look over this arrow. Like I said, they're simple, they all look the same, but some of them have their little nuances, which is why we're doing every mechanism as opposed to saying, hey, just you go and do all your attack open, close kick on your own. Because I could say that and you'd be able to, but there's some nuances here that might make it a little bit harder to follow. It's like, for example, here, what's going on with the pyridine? What did it do in the last roll? I mean, I'm not gonna, my nucleophile, it shows water. I could have also used like NaOH or something, but this one has water over the arrow. So what's going on? Like, why would water even work? If I'm trying to attack that carbonyl and it's not activated and close kick, well, chlorine's a good leaving group, water is excellent. So, in fact, it's even better. So what should I do? I don't want to attack with water. Pyridine's there to help save the day. So remember, pyridine has the benzene ring, only replace one of the carbons with a nitrogen. And let's add our water. So remember, pyridine's a base, and it could just deprotonate. Actually, I should draw this out, right? It can deprotonate and give us hydroxide. So we have a pyridinium plus OH minus. And of course, that's an equilibrium. Now we have a decent base slash nucleophile. Also, we could have used KOH, but I just want to let you know that in case you see the pyridine you need in the water, that's what that's there for, because water is not quite strong enough without a base. All right, so we answered that question. We will do the full mechanism, but you're going to know why now. I just go straight to the OH minus. So that was the point of that little exercise. Let's do a real mechanism. So in other words, take our acid chloride to a carboxylic acid. In other words, we know, we just looked at this, so by analogy, let's draw our carboxylic acid. The chlorine's gone, the OH is in its place. Now remember what this means. This tells me H is off the water, so I have hydroxide available. So with my free hydroxide, I'm ready for business. Attack, open. Close. Chlorine needs to go so that we can be back here. See how short that is? Attack open, close kick, 4 arrows. Okay. We've made, what have we made so far? Acid chlorides into anhydrides, acid chlorides into esters. We got to do the others. Oh no, we did acid chlorides and anhydrides and acid chlorides into acids. Now we're going to do acid chlorides into esters. Okay, so to make an ester, look at the exact similar scenario. Instead of HOH, which is water, we have ROH, meaning pyridine is going to deprotonate, and we're going to the alcohol, and we're going to have not hydroxide, OR minus alkoxide, right? Because it takes off an H. So do not call that hydroxide if you see an alcohol. The R stays, it never goes. Now it is ready to attack, and notice where it comes from. This is our new group, okay? So that new R prime ends up right there. That's on the ester. All right, so let's give this a try. Same old thing. Let's do some real ones. We're going to predict the product. Chlorine's gone. It's a leaving group. Who's in its place? OR from the alcohol over the arrow. That would be ethanol. Ethanol, we get the ethyl ester. Okay. All right. So, because it's exactly analogous, like I said, I want you to try that mechanism in parallel. There's no surprises because water and alcohol act very similarly as solvents, right? So I'm going to put homework there. Feel free to check in with me or the book. It's there. All right. So next one. So we have a lot on our plate to do with these little reactions. We're going to try to get them all together. So amines. Why would I have an amine over the arrow? That's going to be my nucleophile. Chlorine's going to be gone. So amine replaced the chlorine. Notice what we have to have for an amine. It's neutral with 3 bonds. It's going to make a bond to the carbonyl, so it needs to lose something. It has to have an H to lose. Hence, we will never see a tertiary amine because it has no H to lose, okay? So this won't work with tertiary amines. You have to be able to lose an H in order to make space for that new bond. At least one H. So it could be even ammonia. Ammonia is NH3, right? Remember ammonia? So it doesn't even have an R group on it. Or it could be a primary or secondary amine. Why do we need 2 equivalents? Well, what's missing over the arrow that the others had? The others had pyridine there. This one doesn't. Because pyridine's like amine. It has nitrogen, which is a great base in most cases. So it's its own base. So it acts as a base and nucleophile. That's what's special about the amines. Hence the side product you would see, well, actually I should say byproduct, you would see form there. Okay, so what is this going to look like? Can you predict without the mechanism? Can you draw the mechanism? Both are skills we want to do. By analogy, chlorine's gone. Keep your R group, that didn't go anywhere. Chlorine's gone. In its place, who is the nucleophile at the end? So the end's always directly attached to the carbonyl C. Always keep your R group. And then we know nitrogen needs 3 bonds to have a formal charge of 0. So the mechanism would not lead you anywhere else except for 3 bonds. So notice we're missing 1 H. That's because we gained a bond to nitrogen to the other side. So we had to have that H to lose. That will be shown in the mechanism, right? So let's show how we lost that H in the mechanism and how we attacked. So we get to attack right away. Attack, open. Same R group, open to the O-, chlorine, N with 2 H's, hence it's positively charged, ammonium, right? Okay, we can't keep that there. We have to lose that H. So where do we lose it? We need a base. Who's the base? You got it, the starting nucleophile, which is serving as our base now. So here it's a nuke, here it's a base. Serves both roles. Good multitasker. All right, now we're going to keep our R group. We have this extra step to neutralize before we move on. We're not going to close kick a chloride over an ammonium because remember with Cario, charge wins. So ammonium is actually a better leaving group than chloride. So we're not going to close and kick a chloride yet because ammonium would leave instead if we closed. So we don't want that. We had to turn it into amine, which is a terrible leaving group, so that chloride would be better by comparison. Close, kick. So it has that little extra intermediate step to take care of that hydrogen. So like I said, very similar. We have that attack, open, close, kick, but with something in the middle to wrap up the proton transfer we needed to do. Okay, you keeping up? Good, we're on to acid anhydrides. All right, acid anhydrides, remember they have that carboxylate leaving group. Very good leaving groups. All right, so because they're a very good leaving group, but they're not quite as good as the chloride, then the only thing they don't make is the acid chloride. So notice how we're changing directions here. We are done with acid chlorides. You could check acid chlorides off. Now we're doing all the reactions of acid anhydrides, but acid anhydrides do not become acid chlorides. Not directly anyway, not in one step. So we're going to do all the others. So notice there's going to be one missing, one less reaction. Okay, let's take a look and see if we could see what happened here. We can convert them to carboxylic acids by, actually break up quite easily. They're the anhydride of carboxylic acid, they're acid anhydride. So they're the acid without water. So if you want the acid, you add water, right? So if you have a anhydride hydride, then you have an acid because you just negated that, right? So that would make sense to put that over the air with the water. So it breaks up. Let's kind of trace where all those things went. Right there's this guy, and this piece is still there, just here. So the H2O is here. Okay, and you can actually do the reverse in some ways. We'll see that soon. Draw the mechanism. Get a cyclic anhydride. That's a good one. So what does that mean? That means that we have to break, if we look at this, and let's just try to draw it by analogy before we do the mechanism, then we'll prove it with the mechanism. If we break this apart, then one of them, one side gets the OH, and oh look, the other side got the OH. So it's two acids, it's a diacid. So we could do that here. Just because it's a ring doesn't mean we would not be able to work that out. So you can keep it even all bent up like a ring if you want. I think that makes it easier actually. There we go, diacid. So if it's in a ring, we call it a diacid because they're stuck together, they're part of the same molecule. But since they were separate, here they got into separate pieces and we just made two acids. All right, so what's that mechanism look like? Notice we didn't need any acid or base. It works pretty easily on its own. Pick any one of those carbonyls. Attack, open. Okay, let's leave the other one alone. O minus. O attached to water. They just attacked. Okay, so clearly, once again, water is a better leaving group than OR minus. So we've got to take care of that. Make sure water doesn't have the chance to leave by neutralizing this. So anything that has sort of a positive intermediate in these basic conditions, in terms of trying to get a leaving group to leave and make a weak base, you have to deal with that before finishing it off. So we have O minus. Now, this is more reasonable. That's the OH of our first acid. Close. Oh, let's do it in red, like I've been doing. Close. There's no chlorine. Who do we kick? The OR, right? The O carbonyl to make our carboxylate. All right, let's do it. Close, kick. That gets us almost there. So in other words, we have this O minus. And we're home free. I am not going to, we have so many mechanisms to draw, I'm not going to draw acid-base protonation for you anymore for this chapter. I think you'll be okay doing that as well. Okay. So diacid, that was an intramolecular one just for you, a ring, a reverse intramolecular, I guess you could say. Opening a ring opening. All right, let's do the next functional group, convert to esters. So we made an acid anhydride turn into an acid. Now we're going to make an acid anhydride turn into an ester. Look at what that requires. That requires, instead of OH, it requires OR, right? So instead of H2O, we're going to have ROH. Same idea. Let's see where that came from. ROH. And in fact, I'll do it in another color. ROH, R prime rather. It's right here. So the original H, if I circle this, we could think of it all coming from this spot, ROH. So you're basically, instead of adding water to break it up, you are adding an alcohol to break it up. So this piece here and this piece here used to all be together as one, right here, right? Can we do that by analogy? Sure. All right, O, it's broken into two pieces. So one gets the OR. What is our R? Our R is isopropyl. Plus, because remember that's the R prime, plus the other one stays an acid. So we'd say that's a byproduct. This is our goal. Because if we wanted the acid, we would use water, so we didn't have a big mixture. Okay, let's attack. Attack, open. O minus. Methyl's still there. O has its H still. So hopefully this kind of looks familiar. We can't stay there. We can't close kick. We've got to fix it first. So we did our attack, open, but now we have to fix. What do we fix it with? We make sure that we don't have a positively charged group on there that would be a wonderful leaving group that we don't want to have leave. The thing that just attacked needs to be neutralized. So take that and that. Okay. So this could be resolved if we had base conditions. That would help. And that you will see that is a possibility. You can actually do this in base conditions, but you don't need base. It'll work without it because it's that reactive. Okay, so now we have the O minus and right there and the O here. Okay, now we can close kick. Close kick. Wrong. What's wrong with this? Guess where I get to. Go exactly back where I started from. Look at that. Okay, so let's erase that. Who do I close kick instead? Close. I do need to close that one. There we go. Better leaving group anyway. You don't get an OR minus, you get a resonance stabilized leaving group. Okay, now you'll notice this piece right here. Once you protonate that, you get that product. And let's put the green here. Once you close and kick off that, we have this one. I'm glad I did that one with you because I want to illustrate the choices you have sometimes when you close kick. You do have to stop and think, even if it seems simple. That was a good one. Now, amides. what are we going to do to make amides? Well, instead of alcohol over the arrow, we're going to have an amine over the arrow with the corresponding R group that we want. Notice our byproduct again. Here it is. It comes from this guy. All right, but we get to keep the other piece. That's from here. And then the amine, we have, right, NR2. That came from here. Now notice there's two equivalents, so it can be a nucleophile, whenever you see that, and a base. So let's draw that out by analogy. Actually, I need to give myself a little more room. Move that over. Uh-oh, what am I going to do? I got an OH and NH2. What am I going to do? Well, I have half an equivalent of the anhydride, and I have an N versus an O. Who's a better nucleophile? It's okay, because I want an amine, the N's going to attack. So the OH stays, and the N stays as well, but it changes to be modified to have only one H instead of two, because in that third binding site, it now has a carbonyl to make it an amide. Okay, let's show that mechanism. I am going to, just to kind of keep it from being huge, now that we drew the product, I'm going to call this R, so that I don't have to redraw the phenol part of it every single time. All right, so R, in other words, it'll be NH2. So it goes attack, open. R is bonded to the C that has opened up. Then we have, what else is there? Methyl, and the O attached to the rest of the anhydride. I think I attacked the R, but I missed out on the nitrogen. That's no good. That's a key player. Okay, the NH2 is still there. Now here's the R, positively charged. Okay, so now we're going to do what we always do when we see this neutral intermediate. We do not close kick right away. We neutralize it. Who can neutralize it? R, extra equivalent of amine. Neutralize. Okay, we're neutral. Okay, that extra H is gone. Oh, there we go. Now we may proceed with a close kick. Close. Okay, make your decision carefully. Kick. Nope, I'm not kicking off a methyl. No, I'm not going to kick off the amine because I went through all this trouble to add it. Yes, I'm going to kick off the carboxyl group to get a nice carboxylate leading group. Okay, so then we go here, and I'm going to show a little curved arrow coming off. This is a real common thing in a biochemical pathway. As you have this cycle, you might have seen the arrows come off. I'm going to show, we do that with catalytic cycles especially. I'm going to show the byproduct coming off because that's not what we're terribly interested in, but it exists, and I'm acknowledging it, so it helps us kind of understand the mechanism. I'm going to box in my target. We only do this if we want the amide, not if we want a carboxylate. Okay. Good. That is what we are going to do when we start with acid anhydrides. Just wanted to point out, acid anhydride was my carboxylic acid derivative of choice, but notice it's over the arrow. And the amine was on the left side, and in the template, the amine was over the arrow, but the acid anhydride was here. Oftentimes we put the biggest substrate to occupy this open space here. It just makes more sense, and then we put the smaller one over the arrow. But that's not always true. This means these are both reactants, and they could be interchanged. So I could have put the one here and then the other one there. So don't let the order of that throw you off ever. Just wanted to bring that up since I saw that coming through. So we're done with the acid anhydrides. Time for carboxylic acids. Now, carboxylic acids are special because they're acids. They don't just have an electrophilic carbon. So if they have a nucleophile, the nucleophile can also act as a base. And if it acts as a base, we get a good old acid-base reaction. Usually not the goal in this chapter. Acid bases are, that's pretty simple to do with stuff you've learned already. We've made these. So if we're in this chapter, usually our goal is to acknowledge that acid-base reactions happen, so we might have to work with that. It might actually interfere. If we want the nucleophile to act as a nucleophile, we might see some of this product as well. Attack open, right? So that we start to at least get to this point. So this is an acid-base reaction, and this is a nucleophilic addition. Okay, something else to know about carboxylic acids, other than the fact that they actually really stink in real life. All they're really, like, even worse than, amines are pretty bad. It's like a lot of rotting stuff as amines. Carboxylic acids are all the, like, fungus, locker room, socks, shoes, all that kind of smell. And some rotting stuff, like rotting butter is one of the worst smells. It takes a lot for butter to rot, but when it does, it's a bad smell. That's butyric acid right there. An interesting correlation with that, by the way, is as you increase the carbon count, it smells worse. So it's not just the carboxylic acid, it's what's attached. So butyric acid's pretty bad, but octanoic acid, that's like vomit smell. So it's really fascinating how that's related, the chemistry of smell. Okay. As fascinating as that is, we also want to know the reactivity of carboxylic acids. So we know they're not very reactive, right? They're kind of similar to esters. So we can actually turn them into esters. We can't go uphill, right? So when we can make acid anhydrides, which are higher energy, turn into carboxylic acids, but we can't do the reverse. We can't take a carboxylic acid easily and turn it into an anhydride without a lot of effort and energy. So the easier reactions we'll be able to do with carboxylic acids for the most part, or at least predict we should be able to do, is to make them into something also less stable, or excuse me, less reactive, so more stable, esters and amides. However, because of that acid-base reaction I mentioned earlier, we can use that to our advantage. Turn that OH into a better leaving group so that we can access a lot of other functional groups, right? So we can actually make more, like an acid chloride, specifically, by turning the OH into a good leaving group. So a very important reaction that is not parallel to any of the others we've done so far. So the others we've been like, okay, what happens if we add water to this? What happens if we add alcohol to this? Okay, we get this group, we get that group. But now, this is the only one other than nitriles that we're going to use SOCl2 with, thionyl chloride. Let's write that out. Thionyl chloride. Couple reasons this reaction works so well. Actually, I asked that down there. Think about SO2 gas. See that up there? Go ahead and draw your squiggle line. That's kind of rewarding. Entropically very favored. And Le Chatelier's principle removes it from the product mixture as it forms, thus driving the reaction forward. So what's great about SOCl2, which is, by the way, another reagent we use for alcohols converting to chlorides. So it does something similar here. Turns the OH of the acid chloride into a chloride. So recall, ROH can become RCl. Make that longer arrow. Saying out loud. Need SOCl2 over the arrow to become RCl. So that's a alcohol section topic. Why does this work? Because we know that carboxylic acids are not very reactive. There's a way to take advantage. That's the actual electrophilic carbon that's not reactive. But if we take advantage of the acid-base hydrogen that is reactive, then we can kind of work with that. So what does thionyl chloride look like? Looks a lot like a carbonyl. only a sulfur instead. Very reactive one, by the way, with those two chlorines attached. So delta plus, delta minus for this dipole. So we can attack it with the OH on the carboxylic acid. Attack, open, everything attached to it. It opened. Oh, so Cl, Cl. Now I can close and kick. Why am I closing and kicking? Because I said it's just like a carbonyl. We attack open like a carbonyl. It's going to close and kick like a carbonyl. What can I kick? Look at those nice chlorines. However, wait a minute. We don't want to do that. Remember what I said? We got to take care of the H first. It's not, yeah, it's really not going to like that, that H being there. So we got to neutralize that. Honestly, if you did it out of order, it's not the end of the world. But I like to kind of think about which, I would still accept that in other words, but I like to think about which is the better leaving group. So I don't want to have any competition. So because this is a longer mechanism, I'm just going to write minus H plus, so because you know what I did. Took off the H there with a base. All right, now let's do this. Okay, one Cl is gone. Now what? Guess what? The good news is this is going to make a good leaving group. We turn that OH, which is a bad leaving group, into a great leaving group. How is it going to leave? Well, it has to turn to SO2, so I'll show you that. And notice the HCl that forms. So we'll have we lost H over here, so there's lots of proton transferability, going on that can let the HCl form up here. So let's focus on this now. How are we going to get that to go? Well, guess what? Chloride just left. I'm going to use it again. I need chloride, this time to not attack that sulfur, but attack the carbonyl. Attack, open. Sorry if you're running out of space. I think I should have made a little more space for this mechanism. Attack, open. Chlorine's there. Oxygen, sulfur. There we go. Attack, open. Now I'm going to close, kick off, but watch this fancy move. Close. Okay, I'm going to kick in a different way. I'm not going to kick the usual way where the bond lands there. Nope, I'm doing that so don't copy it. It's going to go bond to bond. So all those electrons are going to be shared between the sulfur and oxygen to make a double bond. That's our SO2 gas right there. Sulfur says now I have a full octet from my 2 bonds to oxygen on each side, so I don't need you any more chlorine, so that kicks off. So it's almost like a double close kick, right? If we had to put a name to it, because we closed that instead of, as we kicked it off, it closed and kicked that off. So that would be close, kick. No, close, kick, right? If we had to put words to it. Okay, so that is our SO2 gas. In fact, since it's sulfur, I'll circle it in yellow. There's our SO2 gas forming, right? And now we are all the way back to there. I should actually draw my arrow this way because that was a generic reaction. We're here. So yes, it's a long mechanism, but it's good to see how it works. So it's not a big mystery. The SO2 gas comes off. The thionyl chloride's there to convert the OH into a better leaving group. All right, so that's very useful, super useful. Put a star next to it. Why is it so useful? Because carboxylic acids are not very reactive. Acid chlorides are super reactive. Acid chlorides can do everything. Carboxylic acids can do less. So we will, every time but carboxylic acids are very common, more common than acid chlorides. We see them all over, especially in biochemistry. So if we want to react carboxylic acid, we need to turn it into an acid chloride oftentimes first is a good idea. But there are some things that carboxylic acids can do. So let's look at those other things. They can make an anhydride. After all, that's the name, right? An acid anhydride. It means the two carboxylic acids lost their water to make an anhydride. So they can do that. It just takes heat and them to be in close proximity and usually fixed that way. So you'll see it really commonly with ring systems, right? When you have an acid next to another acid and then you heat, you can drive off the CO2 or the water, not the CO2, excuse me, the water. So let's circle the water that came off here. So H2O right there. And then the oxygen here is this one here in the ring. So you went from acyclic to cyclic. So this could be drawn out, you know, it's not going to always be scrunched up ready for you. You have to be able to turn it into a 5-membered ring or 6-membered ring, a good size ring, because this equals this OH. So what? 3 carbon spacer, right? 1, 2, 3. I know it's a 2 carbon spacer. So 1, 2, 1, 2, and then we have that. So that's how they're typically drawn out. But if you can rearrange an O so that it can attack the carbonyl and get a 5 or 6 membered ring, that can happen. So they have to be decent proximity and have a good ring size. So like this one, for example, these are fixed to already be ready to react. That helps a lot because, like I said, this isn't a fast reaction and it requires some heat. So let's draw that reaction. So in other words, we omit an H2O, anhydride, it's all in the name there, and we get our intramolecular reaction. Okay? So I'll let you work out that mechanism because it's not anything surprising, but intramolecular is really the only way we're going to do that. Notice the 2 examples that were done. It was a diacid, it wasn't 2 acids. Diacid. They're already close together. They're already part of the same molecule. Intramolecular always happens faster than intermolecular. So intramolecular, so diacid in other words, in close proximity to make a 5 or 6 membered ring. So we'll write that down. Also note that heat was added. That helped it progress a lot. Okay. Ester time. You ready for some more Fishers? Not Fisher projection. Not yet. We'll go back to that. Same Fisher though. He's got a reaction too. It's Fisher esterification. So actually, I have a spot to name it on the next page. So we'll get into that. So how does that work? Notice the newness of, so the R group's new, and we formed water. Okay, so water is from, that H goes off to water. But the question often is, which O is in the product and which O is in the water? So in other words, there's 2 O's. Did this O come from that one or did it come from the original? The answer is in the mechanism. Okay, so if I labeled this, I'm going to make one green, and I'll make the other one yellow. I'm going to ask, which one is this one? Green, yellow, okay. Mechanism will tell us. I hope you can make a prediction because the mechanism actually really isn't different than the attack open we've been doing all along. We just have some neutralizing to do along the way because notice the acid is there. So let's do this one step by step since we haven't been adding acid. We've been doing these under basic conditions for the most part. We can predict the product though. We know we have an O and the new R group. So it's that big old guy there. All right, so No big surprises, but the mechanism will reveal this, which will help us work out future problems. So remember, this basically makes RO3H+. I'm just going to call it H+ to kind of quicken this mechanism a little bit. I know you guys know what H+ really means. We're going to activate the carbonyl. We always do that when we have acid present and a carbonyl. Always activate first. So we weren't doing that before. We were in base conditions. Now we're clearly acidic. Must activate. All right, my carbonyl is activated. I only activate it for one reason, and that's to attack it. Who's going to attack it? Let's just call this R right here, so I can not draw it out every time. ROH. Attack. Open. Okay, now remember with acid conditions, it's always a longer mechanism because look at what we have here. We have to neutralize. And that did happen sometimes in the other scenario too, whenever you have the proton transfer to deal with. Now this I am going to do what I just said out loud, exactly a proton transfer. So why would I do that? Because think about what I want to have happen. I want to close and kick. And I do not want to close and kick the alcohol that I just added. So I need to get it off of there, but I want to kick something else. Not this table. Maybe you do, but no, I want to kick the water off. You have to lose water, right? Water is the product right here. So got to kick off the water. All right, so one of those OHs, it's coming for him. Let's see, I'm just going to randomly choose this one. This is the one that gets hit. All right, so now, remember, that's what's going on in a proton transfer. I move the proton. It represents two separate steps of the mechanism, but in advanced cases, it's officially okay to do this as one step. There's no arrows to push though, because the arrows are omitted because it represents two steps. So in other words, I don't want this here. I want it over here so I can lose the water and keep this. Now I may close kick. Let's do it. Close. Goodbye, water. All right, we are so close, but we have that proton left, which is why I am not going to belabor the acid-base proton transfer there, but so I'll write -H+. I want you to notice that the R got filled in, okay? So this is the Fischer esterification under acidic conditions. So Fischer, it's actually a really nice reaction. We do this in lab. Actually, we do it in 211 lab too. So it's, even though they're, they don't know that mechanism yet, Fischer, because it works really well. Esters, unlike carboxylic acids, smell very nice. They're in most perfumes. The one we do in our lab is actually banana oil, isoamyl acetate. So a lot of fruit, actually, not just banana has that, pears. So a lot of those nice, pleasant aromas come from esters. Fascinating how that one little change, replace that H with an R, and you have a better smelling compound right there. Okay, couple notes about good old Fischer esterification. We needed that acid. Why did we need the acid? We need to activate our carbonyl. Esters aren't very reactive, so we're making something stable here, but notice we're starting with something not very reactive. So we need to make it more reactive by activating it. What's wrong with a base? Carboxylic acid, that word, acid. So you're not going to see this work so well with base. Carboxylic acid is formed so let me just write out this equilibrium. So if we're starting with a carboxylic acid and we have a base condition, we're going to deprotonate the acid before we ever do anything else. And we don't want that to happen. So that's not our goal. We must have an acid. Okay, so that's really short, right? That was the carboxylic acid things they can do. We can turn them into esters. We can dehydrate them under intermolecular conditions. But then we can only do everything else if we turn it into an acid chloride. And at that point, it's on the acid chloride part of the roadmap. So that's kind of nice to remember that. Okay, now what can esters do? What can ester do? They can form, they can be hydrolyzed to go back to the carboxylic acid. They could also form amides because those are even less reactive. So as I promised, the reactions get shorter and shorter. So let's look at how we do hydrolysis, ester hydrolysis. Okay, so it can be done in both conditions, acid and base, right? So carboxylic acids, they're going to have the same product. Esters will become carboxylic acids plus the alcohol that it kicked off. Let's do the base one. I'll let you try the other one. No surprise there. It's similar to, if we break it up one way, we can break it up the other. So think about the fact you have to break it up. You have to attack that carbonyl. So if you have acid, you're going to activate first. If we have base, we don't need to. There's a reason I'm doing this one. It's a very famous reaction. It has another nickname. So we'll do attack open. OH, OR. Yeah, I really don't need to do this for you guys. You guys could do this on your own, but I want to bring up this fancy name for this one. Close, kick. I mean, and there you are. You got this one. Then you protonate the other side, and you have your ethanol, right? Okay, so when you hydrolyze an ester with a base, so basic hydrolysis of esters, has its own special name that you want to recognize. That name, you want to know that word. Saponification. That's because it has a long history of being something very important for civilization. So sapo in Latin, Latian. I'm thinking of saponification. Latin for soap is sapo. So that's where the saponification, that sounds like such a long word, but that's the etymology of it. So soap is made from saponification. So here's a little side note for fun. Actually, the chemistry of soap comes up quite often because there's a lot of things we take advantage of to get soap to work. So our ancestors that made their own soap out of necessity, or maybe recent for fun. I've had students who like to do it for fun because it's got a lot of chemistry in it. But the old way, before you get the soap kits and stuff, was to like save your fat from the meats, like lard, essentially. That's where the triglycerides come from. Then they would save their ashes from the fires and extract out the lye. Lye is basically, or they sometimes call it potash, but it's essentially what you're trying to get in there is the basic. What do we have? We have a triglyceride, which is a triester. We have an excess of base. You get hydrolysis into the fatty acid component, because a triglyceride is 3 fatty acids. I mean, you say, wait a minute, what's the Na? That's the conjugate base of the acid. So if we just protonate that, we have a fatty acid. And then the alcohol, it's a triol, came from the middle portion. So this is our ROH and our carboxylic acid. So we'll talk more about soap again when we get into the biochem section, but it's kind of interesting that it has that rich history. So saponification that's why it has its own special name for that reaction. So make sure you're comfortable with that terminology. What else can esters do? They can make other esters. So in other words, you can start with one ester and swap out, flood it with a bunch of alcohol with a different R group, like let's say it has R prime right there, and then you want R double prime. Then you're going to have the new R group. So with that in mind, what do we expect? Well, we learned from the last mechanism that the nucleophile is the alcohol, right? So the nucleophile is the alcohol. So this comes from the R double prime O, comes from here. And we lose our leaving group here. So can we predict our product? Transesterification. O, instead of O-ethyl, find your new R group, OCH3, or O-methyl. You can draw that in. So transesterification. All right, so in basic conditions, how does that mechanism work? We need if we have a base, we're having it there to make a better nucleophile if it's not going to be the nucleophile itself. So to avoid attacking with hydroxide, you would need, it's actually better form to have RO minus for this reason. That's okay. So, but that's because we're going to have CH3O minus, and usually that would be in ethanol. So, or methanol. All right, so you have an equilibrium there. All right, so now that's our nucleophile. Attack, open, pH, O minus, and OCH3. Where's the rest? I still have this on there. O-ethyl. O-ethyl. Let's add it again. Now we're going to close and kick. Kick off O-ethyl. Yes, bad leaving group and all. Because we're in basic conditions. Okay, so pretty short and sweet. That's basic hydrolysis of an ester and transesterification. Those are the two reactions we could do so far. There's only one more. Amides. We can form amides. So let's do that. How are we going to form amides? Look at this familiar pattern. We don't need to add a base because it's its own base. So we just add the extra equivalents to make sure we take care of that. We're going to use ammonia this time for our example. Attack, open. What's that going to look like when we're done? I always kind of like to predict the product to see if I match it, if it's not drawn in yet. So remember, you're always going to lose an H during this process in order to allow for that degree of freedom for the nitrogen to make that bond to carbon. So that's what I'm working toward. Attack, open. Now it is attached. This unhappy ammonium, it's not going to stay that way. We're going to lose that proton. There's some flexibility here. Different books will do different things. They may not like this step. I'm a little hesitant with it because nitrogen is a stronger base, but I'll run with it. In other words, what we're working for is getting that alcohol to be a good group. But like we said, they're not very reactive to begin with. So that's what makes it kind of difficult. Other books would say, so this is one way. Other books would say, just neutralize that, and then who cares, let that leave. Fine with both, because they're reasonable. We're splitting hairs at that point. All right, close, kick. In another class, it wouldn't be splitting hairs. There's good mechanistic focus on that, but think about the quantity reactions. So I would accept both of those because they're totally reasonable. They get us to the end with following lots of the established rules of mechanism writing. And there we go. Okay, that's a reasonable mechanism. That is it for esters. What can amides do? Nothing, almost. Amides are our last one. Amides can be hydrolyzed, but they're not easy to do anything. They're really stubborn. That's a good thing. You know why? Our amino acids, kind of rely on amide bond formation. So we need them to be stable. But nonetheless, amides only react under strong conditions. So high heat or, acid, base, it's not going to do anything in a neutral condition. So whether you're in a lot of acid or base, you can hydrolyze an amide. So in other words, then you can neutralize this and end up with the carboxylic acid. So workup. Some source of proton workup will get you to the acid. So you can convert amides to acids. All right. So I say draw the mechanism on your own for extra practice. I will do the hydrolysis of the amide with you by drawing the product. Notice the instructions. We've had a lot of parallel themes in the mechanisms, so I want you to draw the mechanism on your own for extra practice, but let's take a look. Kind of think through the general idea. It's a tack open close kit because we keep the carbonyl, but we replace it with an OH. Our group always stays. So easy, right? You just take the amide, nitrogen's gone, OH in its place. But there's the acid conditions down here. Here's the base conditions. Try the mechanism for both. And I'm going to assume that we kind of understand that to build up to some later reactions. What I would like to do at the very end is put this all together. Okay, so I'm going to encourage you to pause. And I'm going to sit and disappear, fill out this chart, and then I'm going to ask you to get another piece of paper. Because in addition to the roadmap that's in the back of the textbook that I showed you, the Klein book, I also want to rearrange it another way to show you a different way to set up a roadmap that's kind of unique to this chapter. But I think it's helpful. So there's a chart that might help. So think about this. This will help you get ready in roadmap mode. So go through what we just did and see if you could fill in how they react. In other words, do they yes or no, like check or not check. So in other words, acid chlorides don't turn into acid chlorides. There's an X there. But you could write yes or no or check or X, something like that. So fill this out, grab a piece of paper, come back to see this all filled in with me. Okay?